Have you ever wondered how we can control the massive, powerful flow of electricity from a distance without actually touching the current itself? I mean, really think about it. How do you build a tiny device that can flawlessly restrict or open the floodgates of electrons using absolutely nothing but an invisible electric field?
Well, welcome to the Explainer. Today, we're unraveling one of the absolute most elegant components in modern electronics, the Junction Field Effect Transistor, or the Jfet. If standard transistors are kind of the heavy lifters of the electronics world, the Jfet, it's the precision instrument. It operates so uniquely that engineers often consider it the true solid-state equivalent of the classic vacuum tube.
So, here's our roadmap for today. We're going to start with enter the field effect transistor, then dive into how the Jfet works. Next, we'll compare Jfets versus bipolar transistors, break down their key characteristics, look at biasing circuits, and finally, wrap up with some real-world applications.
All right, let's kick things off with Section 1, Enter the Field Effect Transistor.
To really appreciate the Jfet, we first kind of have to understand the major headaches that engineers faced back in the early days of solid-state electronics. You see, before the FET came along, standard bipolar junction transistors were the undisputed heroes of the industry. They literally revolutionized everything. But they had two really frustrating limitations. First, because their emitter junctions were forward biased, they had extremely low input impedance. Basically, they drew way too much current from preceding circuits, dragging them down in a process known as loading. Second, because of how they threw electrons across those junctions, they were remarkably noisy.
Okay, so enter the field effect transistor, a total game changer. While they look pretty similar to early transistors on the outside, their internal operation is wildly different. The FET acts incredibly similarly to that classic vacuum tube we mentioned earlier. Because of how it's built, it inherently boasts a massive input impedance. We're talking sometimes over 100 megaohms. It draws practically zero current from the source, and it's beautifully quiet. It was exactly the high-impedance, low-noise savior that the electronics world desperately needed.
Moving right along to Section 2, how the Jfet works.
Let's do a quick anatomical teardown to see exactly what makes this thing tick. A Jfet basically consists of a main channel of semiconductor material that can be either N-type or P-type with two basic connections, the source at the bottom and the drain at the top. But the real magic, that lies in the third terminal, the gate. Now, if you're just looking at a flat diagram, you might think the gate is just two little patches slapped on the sides. But actually, the gate material completely surrounds the main channel, almost exactly like a belt wrapped tightly around a waist.
So how does it actually control electricity? Well, let's use a classic garden hose analogy here. The channel of the Jfet is the hose itself. The voltage you apply across the drain and the source, that's the water pressure pushing through the hose. The gate, then, is your hand. When you apply a reverse voltage to the gate, it creates a depletion layer, which is an electric field that physically pushes into the channel. It's exactly like your hand squeezing the outside of that garden hose to restrict the flow of water.
If we visualize this squeezing effect, you'll see that as we increase that reverse voltage on the gate, those depletion layers extend further and further into the channel. Eventually, if you apply enough reverse voltage, those two layers physically touch right in the middle. The channel becomes completely pinched off, stopping the flow of electrons entirely. There's no physical contact. You're controlling the current purely through the invisible pressure of an electric field. It's brilliant. Which brings us to Section 3, Jfets versus bipolar transistors.
Fitting the Jfet directly against the older BJT really highlights a stark contrast in how they take commands. The BJT needs an active current, what we call IB, flowing straight into the base to operate at all. It actively consumes power to work. But for the Jfet, the gate current, IG, is effectively 0 amps. Sure, it might draw a few microscopic microamps in reality, but for all intents and purposes, it draws absolutely nothing. It just sits there, feeling the voltage.
And this highlights the absolute core difference between the two. The old BJTs are called bipolar because both holes and electrons play a part in conduction, making them inherently noisy and current-controlled. The Jfet, on the other hand, is unipolar. Conduction happens purely through one single type of material, totally avoiding those messy, noisy junction transitions. This makes it voltage-controlled, remarkably high impedance, and whisper quiet. It acts just like a digital water valve that takes zero physical effort to turn.
Let's dive into Section 4, Key Characteristics and Parameters.
Now, if you really want to understand a Jfet's performance, and we're going to skip all the textbook math and complex formulas here, the very first crucial concept you need is the pinch-off voltage. Going back to our garden hose analogy, this is the exact precise moment you've squeezed the hose just enough so that no matter how much you crank up the water pressure at the faucet, the water flowing out the other end remains at a steady, maximum, completely unchangeable rate.
You can really see this crucial point as voltage increases. Initially, the current rises rapidly. That's you turning up the water pressure. But right at the pinch-off voltage, VP, the current just flattens out completely. This flat plateau area is called the active region. And as long as you keep your voltage within this flat zone, the Jfet behaves as an absolutely perfect constant current device.
The next big parameter to know is transconductance. You can just think of this as the sensitivity of our valve. A higher transconductance number simply means that a tiny, barely there squeeze of the gate voltage creates a massive, dramatic restriction in the current flowing through the main channel. It basically tells us just how effectively the gate is doing its job.
All right, Section 5, Biasing and Circuit Configurations.
So how do we actually wire these brilliant little components up in the real world to make them do useful work for us? Well, the absolute golden rule of wiring a Jfet is this: you must keep the gate reverse biased. Remember, its whole superpower is its incredibly high input impedance, and that only exists if current isn't allowed to flow forward into the gate. Biasing is simply the way we set up our external resistors and voltages to guarantee that, no matter what the incoming signal does, the gate never ever lets current slip backward.
Now, the two most common ways to achieve this are the self-bias method, which is super simple and uses just a single resistor on the source, and the voltage divider method. We're skipping the complex equations, but basically, the voltage divider provides incredible stability for the circuit's operating point, even though it requires an extra resistor at the input. Both methods achieve the exact same safety goal for the gate.
When we build this into an actual working amplifier setup, it gives us the common source connection. Honestly, it's by far the most popular arrangement in all of electronics. We feed the weak signal into the gate, and we pull the massive amplified signal right out of the drain. The source terminal at the bottom just acts as the common ground for both sides. It provides fantastic voltage gain, though it is worth pointing out that it flips the signal completely upside down, giving it a 180-degree phase shift.
Finally, let's wrap up with Section 6, Real-World Jfet Applications.
So, where do we actually find these incredible little components hiding in our modern technology? Well, one of its most elegant uses is as a buffer amplifier. Imagine you have a very delicate first stage of a circuit, and then a really power-hungry second stage. If you connect them directly, the heavy second stage will literally drag down and ruin the signal from that delicate first stage. But if you insert a Jfet buffer in between them, it acts as a perfect shield. It effortlessly reads the signal from the first stage without drawing any current at all, and then robustly powers the second stage.
To quickly summarize its top-tier applications, Jfets are the undisputed champions for buffer amplifiers because of that light loading we just talked about. They are also absolutely crucial in phase shift oscillators because they maintain total stability without draining the circuit. And perhaps most impressively, they are the go-to component for radio frequency, or RF amplifiers. Because they operate without all that messy junction noise, they are absolutely perfect for catching incredibly weak, faint signals from antennas without drowning them out in static.
We've seen how the Jfet revolutionized electronics by perfectly mimicking a vacuum tube inside a tiny, silent solid-state block, controlling immense power with nothing but the ghost of an electric field. But I want to leave you with this thought today. If the Jfet is the perfect solid-state valve, what happens to the field effect when our microchips shrink so far down that the channels are only a few atoms wide? How on earth will we build the valves of the quantum future? Something to chew on. Thanks for watching this explainer, and we'll catch you next time.